On September 2008, after years of anticipation, the Large Hadron Collider, the most advanced high-energy particle collider in the world, was brought online. Constructed by the European Organization for Nuclear Research, its building process was meticulous and complex. Over time, the LHC has greatly expanded our knowledge of the universe. Recently, however, a surprising development has left physicists perplexed. They actually made a terrifying new discovery about antimatter at CERN. The details of this shocking discovery were recently disclosed by famous physicist Brian Cox. This discovery has sparked a flurry of theories within the scientific community. What occurred that was so startling, and what might it mean for both the current research and the future of scientific exploration? Stay with us as we dive in.
CERN have managed to capture atoms of antimatter hydrogen. Now, antimatter, I should say, gets made all the time. It gets made in these cosmic ray collisions. We've been using it for years in particle physics experiments, but we've never been able to build atoms of it. So get an antiproton and put an anti-electron in orbit around the proton for any length of time. So the great advance is that we've worked out how to do that. And that's interesting because once you've got a hydrogen atom is the best understood, probably the best understood system in the universe. We understand how hydrogen atoms work with extremely high precision because they're very, very simple. So by building anti-hydrogen atoms, we can look in detail at the way the differences in behavior, if there are any differences, between matter and antimatter. And that's an enormous question because we don't know whether they behave in precisely the same way or whether there are tiny differences. We think there may be tiny differences because we need to explain why there isn't really very much antimatter in the universe today when it was probably made, well, it must have been made in equal amounts at the Big Bang. So that's a big question. Could it be dark matter? So dark matter, the other great question, which is a bit more, perhaps a bit easier to see that we might get an answer to, is that another 26% of the universe is made up of something called dark matter. There's a lot of stuff we can't see and we don't know what it is, and it's something like 96% of the universe. So that's kind of a bit embarrassing in a complete theory of the universe. Some of it we think is in the form of dark matter. We're very sure actually that it isn't antimatter because you'd see it bumping into matter and giving out lots of energy and light, and we don't see that. So we think it might be something else, it must be something else, and we think there are certain kinds of particles we think we might find at the Large Hadron Collider which are very strong candidates for that. So it's not dark matter, but it's interesting because we want to see if there are differences in behavior between antimatter and matter.
Have you ever imagined a colossal machine stretching across two countries and extending deep beneath the Earth? Enter the world of the Large Hadron Collider, a marvel of engineering created by CERN. This is not just any machine. It's the largest and most powerful particle collider in the world. And its story is as fascinating as its function. CERN, the European Organization for Nuclear Research, stands as a symbol of international collaboration and scientific exploration. Its roots date back to the post-World War II period. As Europe began to recover from the war, there was a growing belief among scientists and policymakers that collaboration was essential for rebuilding the continent's scientific capabilities. In 1950, physicist Louis de Broglie suggested creating a joint European laboratory to boost scientific progress and foster peaceful cooperation. Shortly after, in 1952, 11 countries signed the CERN Convention, founding the organization. By 1957, CERN was operational, located on the border between Switzerland and France. The organization's main goal was to study atomic nuclei and their components, which required particle accelerators. These massive machines accelerate particles to near light speeds, colliding them to uncover fundamental insights into the universe's building blocks. In the 1980s, the concept of the Large Hadron Collider began to take shape. As scientists' ambitions grew, so did the need for a more powerful machine to explore the fundamental mysteries of matter. The LHC was designed as the world's largest and most powerful particle accelerator, featuring a 27-kilometer ring of superconducting magnets and detectors. Construction started in 1998 and was a remarkable engineering achievement. Located 100 meters underground, this enormous ring required the efforts of thousands of scientists and engineers from around the globe. It took a decade to complete, and by 2008, the LHC was set to begin its particle collisions. But why was it built so deep? Besides protecting the collider from surface disturbances, the depth helped avoid the complex terrain of the Jura Mountains. This design choice eliminated the need for a massive vertical axis shaft, saving significant costs. After all, it's more practical to use space underground rather than purchasing expensive surface land. So what exactly does the vast underground ring do? In 2010, it achieved its first particle collision at an astounding energy level of 3.5 tera-electron volts per beam. To put that into context, this is nearly 4 times the previous world record, and it was just the start. With subsequent upgrades, it now reaches an even more impressive 6.5 tera-electron volts. Picture 2 beams of particles racing close to the speed of light before colliding. That's the Large Hadron Collider for you. It has 4 specific points where these high-speed particles intersect and collide. Around these collision points, 7 detectors are positioned, each designed to observe and analyze the various phenomena resulting from these collisions. Typically, the LHC collides proton beams, but once a year, for a month, it shifts its focus to heavy ions like lead. It's like the machine's annual special event. You might wonder why all this effort is put in. The answer lies in our quest to understand the universe. Physicists are using the Large Hadron Collider to explore some of the most complex theories in particle physics. They're particularly interested in studying the elusive Higgs boson and investigating the possible existence of a wide range of particles predicted by the supersymmetric theories. Have you heard of hadrons? These are tiny subatomic particles composed of even smaller components called quarks, which are the fundamental building blocks of protons and neutrons. The LHC is designed to collide with these hadrons, generating byproducts that exist only for brief moments and cannot be studied otherwise. Each collision in this enormous underground ring resembles a mini Big Bang, allowing scientists to gain insights into the fundamental nature of the universe, its building blocks, and the forces that hold it all together. Built between 1983 and 1988, this underground tunnel measures a substantial 3.8 meters in width and is reinforced with concrete. Above ground, there's a facility housing critical equipment. Picture a room filled with intricate control electronics, compressors, ventilation systems, and cooling units. Here's where it gets impressive. The LHC generates around 15 petabytes of data annually, a staggering volume to manage. An international team developed a specialized computing grid for the LHC, which is an impressive technological achievement in its own right. The primary goal of the LHC is to reveal the secrets of the elusive Higgs boson, a particle predicted by scientists but never observed due to its high mass. The LHC aims to produce several Higgs bosons every minute, akin to setting a trap for a rare creature long believed to exist but never captured. And the LHC's efforts don't stop there. In addition to searching for the Higgs boson, the LHC delved into other unexplored areas of physics, looking for supersymmetric particles and other hidden aspects of the universe. But it wasn't without challenges. Shortly after starting in 2008, the LHC experienced a major issue when a magnet malfunction caused significant damage, delaying tests for over a year. Nevertheless, once it resumed operations from 2009 to 2013, the LHC achieved groundbreaking discoveries, including the long-sought Higgs boson. Following its first successful run, the LHC underwent upgrades and went into hibernation, returning in 2015 for its second run until 2018. After another break, it restarted in April 2022 with an enhanced beam energy of 6.8 tera-electron volts. Its third run, expected to continue until 2026, has already produced some remarkable results. On July 7th, during this run, something extraordinary happened. Picture Earth's magnetic field as a protective shield around our planet. On that day, a mysterious crack appeared in the bubble, and it didn't just vanish quickly. It remained open for an impressive 14 hours. Picture a window left open on a stormy night, letting in all the cold wind. This crack allowed a surge of solar winds from the sun, leading to intense geomagnetic storms. The outcome was stunning displays of auroras in the sky. Fans of the television show Stranger Things might recall Vecna, the villain, and some humorously speculated that Vecna could have come through this crack. Well, that's just a fun theory. The auras were indeed a spectacular sight. But what caused this crack? It was due to a co-rotating interaction region from the sun. CIRs are large plasma structures formed when the solar winds of different speeds interact. Think of it like 2 rivers, one slow and one fast, coming together to create a turbulent waterfall. These CIRs, along with other solar phenomena like coronal mass ejections, are ejected from the sun toward Earth. When they collide with our planet, they produce a light display known as the auroras. On the early morning of July 7th, a CIR impact resulted in a prolonged geomagnetic storm. The National Oceanic and Atmospheric Administration noted that this storm was intensified by a prior coronal mass ejection. Should we be concerned about these events? Interestingly, experts say no. Earth's magnetic field, our protective barrier, frequently experiences such disruptions, but they typically close quickly. Recent occurrences, however, show that these disruptions can last for hours. Picture living in a house during a storm with a window that occasionally gets stuck open. Although most of the storm is kept out, some rain might damage the furniture. Similarly, while our magnetic shield blocks most space storms, a bit of energy can still get through. This can sometimes interfere with things like satellites, radios, and power systems. In 2003, Harold Frey compared our magnetic shield to a drafty house. Most storms are kept at bay, but occasionally some energy manages to seep through, sometimes just enough to create a sky spectacle or interfere with our technology. Fortunately, there were no radio blackouts or power outages. Instead, this cosmic event offered a breathtaking surprise for those in Canada and the US. Spectacular northern lights. But there's more. Scientists have revealed that the sun is becoming more active than expected for this stage in its cycle. Now, what does that mean for us? It means your chances of seeing an aurora have significantly improved. Over the next 3 years, anticipate more frequent displays of vibrant colors in the sky. And speaking of groundbreaking scientific discoveries, let's discuss the Large Hadron Collider. Consider the LHC as a colossal microscope that allows scientists to examine the smallest particles in the universe. In July 2017, the LHC made several remarkable discoveries, including insights into the properties of the Higgs boson. By 2021, the LHC had identified 59 new hadrons. Then, in July 2022, it detected a new particle called the pentar, formed from unique quark combinations. Despite its advancements, the LHC, like all high-tech devices, faces challenges over time, leading to decreased efficiency in producing groundbreaking results. However, scientists are addressing this with an upgrade to the LHC, known as the High Luminosity Large Hadron Collider, which began in June 2018. Now, this upgrade aims to enhance the LHC's ability to detect rare cosmic phenomena. So, what makes the LHC notable? Its initial run led to the discovery of the Higgs boson, and the second run provided deeper insights into this particle. With its third run set to conclude in 2025, scientists at CERN are anticipating a surge in data and discoveries. The Large Hadron Collider at CERN is preparing for an exciting new phase. By 2029, this massive machine will be colliding particles at rates 10 times more intense than before. The excitement continues as this phase, expected to last until 2042, will generate datasets that are 10 times larger than those from its third run. Now, if you're curious about why this matters, let's explore the world of proton collisions. Imagine protons as containers filled with colorful jelly beans. Inside these containers are smaller particles called quarks, held together by even tinier particles known as gluons. It's like a dynamic dance of nature's smallest elements. Imagine 2 bags of jelly beans colliding. Often, the jelly beans, or particles, scatter and reform into familiar patterns. But occasionally, something extraordinary occurs. 2 quarks or gluons collide directly. This collision compresses all their energy into an almost infinitesimal point before explosively releasing it. It's during these rare, high-energy events that physicists might glimpse the deeper secrets of nature. The challenge arises in the LHC, where protons collide an astonishing 40 million times per second. To put this into perspective, it's like trying to capture a unique moment from a firework display that never stops. Each collision produces data equivalent to 20 times the size of a typical smartphone photo. Collecting this data would fill a database with 1 million gigabytes every second. Amid the 40 million events per second, most are ordinary. Amidst the vast amount of data, there's just one significant Higgs boson event. So how do scientists manage to sift through all this information? Enter the trigger, an advanced computer system that functions like a selective photographer, capturing only the most intriguing collisions, just a few hundred per second. These selected moments are the ones scientists will later examine in detail, hoping to uncover the universe's secrets. The LHC acts as a giant microscope, delving into the fundamental components of our universe. Think of it as a massive machine aiming to unlock the mysteries of how everything is constructed, with the primary goal of discovering previously unknown particles that might reveal new cosmic insights. Some of these elusive particles could be extremely heavy, like heavyweight champions of the universe, breaking down into smaller particles with enormous energy. However, most scientists think that during the LHC's third run, or Run 3, we might not actually detect these massive particles. Instead, we might uncover clues or indirect evidence, akin to finding a map instead of the treasure itself. These clues could point to more significant discoveries in future experiments. Then there's dark matter, the mysterious substance that makes up a substantial portion of the universe, but remains invisible. Some new particles might be linked to dark matter, but they're so elusive that they rarely reveal themselves directly. It's similar to trying to see the wind. You can't see it, but you can certainly observe its effects, like the rustling leaves. In the LHC, we look for particles behaving unusually, which might indicate the presence of these hidden particles. The challenge is that these signals are often so faint that our detectors can miss them, like trying to hear a whisper at a rock concert. With improvements in Run 3, we aim to enhance our detectors to catch these subtle signs more effectively. And guess what? There's more to come. Plans are in motion for an even larger and more ambitious machine, the future Circular Collider. Think of it as the LHC's larger counterpart, potentially costing between $9 and $21 billion. However, not everyone supports this ambitious project. Some argue that given its high cost, we might be better off exploring other major scientific projects. For example, consider a massive radio telescope on the far side of the moon, or perhaps a space-based device to detect cosmic ripples known as gravitational waves. Sabine Hassenfelder, a prominent physicist, suggests that this new large machine might not reveal the breakthroughs we're hoping for. It's akin to investing in a high-power telescope that might not reveal new stars. However, with the LHC gearing up for its third run, and potentially a fourth, there's so much to look forward to. It's like being in the middle of a cosmic mystery, gradually uncovering clues, with each phase offering more insights. Imagine it as episodes of an exciting series that we're about to binge-watch. Recently, an anomaly in Earth's magnetic field that lingered longer than expected was like finding an unexpected hidden door in your home. What other discoveries might be in store? According to experts like Max Laughlin, we might be facing a significant issue. Laughlin's theory proposes that experiments conducted at the European Organization for Nuclear Research could have inadvertently shifted humanity into an alternate universe, leading to what is known as the Mandela effect. He suggests that the high-energy particle collisions at CERN might have created a disturbance in the fabric of space-time, nudging us into a slightly different version of our universe. The Mandela effect, named after the mistaken belief that Nelson Mandela died in prison during the 1980s rather than in 2013, describes a situation where many people remember events or details differently from how they actually happened. Supporters of this theory argue that such widespread misremembering is not just a memory glitch, but evidence of our movement to an alternate reality. While Laughlin's theory is thought-provoking, it remains speculative and has been met with skepticism from many in the scientific community. CERN's experiments are at the forefront of scientific research and push the very limits of our understanding of the universe, but there's certainly no solid evidence to suggest that they can transport us to a parallel reality. Such theories can cause public concern about safety. At CERN, safety is a top priority in all aspects of its operations. Strict protocols are in place to limit radiation exposure, with personnel using dosimeters and areas with radiation hazards being closely monitored. Advanced engineering designs and shielding materials are employed to contain radiation. Chemical safety is also a major focus, with careful handling and disposal of hazardous substances. Electrical safety and fire prevention are rigorously maintained through regular inspections and adherence to international standards. CERN also ensures the well-being of its staff with comprehensive training and safety drills for emergencies, including fires, chemical spills, or radiation leaks. On-site medical services are available to address any health issues promptly, and environmental safety measures are strictly observed. CERN is a hub of scientific inquiry and innovation. Beyond its role in exploring the fundamental particles of the universe, it has also become a symbol of international collaboration. Scientists and engineers from all over the world come together to work on groundbreaking projects. This global cooperation is a testament to the shared quest for knowledge that transcends national boundaries. One of the key aspects of CERN's operation is its dedication to maintaining transparency and openness in its research. The facility regularly publishes its findings and shares data with the global scientific community. This openness not only fosters trust, but also accelerates scientific progress by allowing researchers from different fields and institutions to build upon each other's work. By making their data and results available, CERN helps to democratize access to cutting-edge research and encourages a collaborative approach to solving some of the universe's most profound mysteries. The impact of CERN's research extends beyond the realm of particle physics. Many technological advancements have emerged from the development of its experimental tools and techniques. For instance, the World Wide Web was initially conceived and developed at CERN as a means to facilitate communication between scientists. What started as a tool for researchers has since evolved into one of the most transformative technologies of the modern era, illustrating how fundamental research can lead to widespread societal benefits. In addition to its scientific contributions, CERN is also involved in educational outreach and public engagement. The facility offers various programs aimed at inspiring the next generation of scientists and engineers. Through guided tours, interactive exhibits, and educational workshops, CERN aims to make complex scientific concepts accessible and engaging for people of all ages. This commitment to education helps to cultivate curiosity and enthusiasm for science, which is crucial for fostering future innovations and discoveries. Another important aspect of CERN's work is its focus on ensuring the safety and well-being of its staff and the surrounding environment. The facility adheres to stringent safety protocols and environmental regulations. Regular safety drills and comprehensive training programs are in place to prepare for potential emergencies. Additionally, CERN conducts thorough environmental impact assessments to minimize the ecological footprint of its activities. This proactive approach ensures that the research conducted does not adversely affect the local environment or community. Looking ahead, CERN's future projects promise to further expand our understanding of the universe. The planned Future Circular Collider, which is said to be even larger and more powerful than the LHC, represents the next step in probing the deepest aspects of particle physics. The FCC aims to explore new energy scales and potentially discover new particles or phenomena that could revolutionize our understanding of the universe. As ambitious as it sounds, this project underscores CERN's commitment to pushing the boundaries of knowledge and exploring the unknown. So thanks for watching this video. We would love to hear your thoughts in the comments below. Please stay tuned for more videos.